What happens at the event horizon of a black hole? The event horizon. It's the defining boundary of a black hole, the point of no return. Cross it and you can never come back. Not with rocket engines, not by teleportation, not even if you could somehow travel faster than light. Once you're inside, all roads lead to the singularity. But what actually happens at the event horizon? Is it a violent, fiery boundary that incinerates anything approaching? Is it a wall you can see and touch? Or is it something far stranger, a purely mathematical surface where the laws of physics undergo a fundamental shift? Today we're exploring one of the most mind-bending concepts in all of physics. We'll examine what the event horizon really is, what someone falling into a black hole would experience, how time and space behave near this boundary, and why some of the most puzzling paradoxes in modern physics arise from trying to understand what happens there. This journey will take us into the realm of Einstein's general relativity, quantum mechanics, and the frontiers of theoretical physics, where our current understanding breaks down. Let's cross the threshold. Defining the event horizon. Before we can understand what happens at the event horizon, we need to be precise about what it is. The event horizon is not a physical surface. There's no membrane, no barrier, no structure made of matter or energy. It's a boundary defined purely by geometry and causality. Specifically, it's the surface from within which no causal influence, no signal, no information, no matter can ever reach the outside universe. To understand this, we need to think about light cones. In relativity, the future of any event is described by its light cone, all the events that could potentially be influenced by what happens at that location. Similarly, the past light cone contains all events that could have influenced that location. As you approach a black hole, these light cones tilt. Gravity warps space-time, and the warping affects the geometry of possible trajectories. Closer to the black hole, the tilt becomes more extreme. At the event horizon, the light cone tilts so dramatically that even light rays pointed directly away from the black hole can no longer escape. The entire future light cone points inward toward the singularity. This is what makes the event horizon special. It's the location where the geometry of space-time changes from escape is possible to escape is impossible. It's a one-way membrane in space-time itself. For a non-rotating, uncharged black hole, a Schwarzschild black hole, the event horizon is located at the Schwarzschild radius, given by the formula R equals 2gm over c squared, where g is the gravitational constant, m is the black hole's mass, and c is the speed of light. For a black hole with the mass of our Sun, the Schwarzschild radius is about 3 kilometers. For the supermassive black hole at the center of our galaxy, with 4 million solar masses, it's about 12 million kilometers, roughly the radius of Mercury's orbit. The important point is that the size of the event horizon is proportional to mass. Double the mass, double the radius. This has profound implications for what happens at the horizon. The principle of equivalence. Nothing special locally. Here's something that might surprise you. According to general relativity, there's nothing special about crossing the event horizon. At least not locally, not from the perspective of someone falling through it. This follows from Einstein's principle of equivalence, which states that in any small enough region of spacetime, the effects of gravity are indistinguishable from acceleration. More specifically, if you're in free fall, not resisting gravity with rocket engines or other forces, you experience no local gravitational effects. You're weightless, just like astronauts on the International Space Station. Now, imagine you're falling toward a black hole. As you approach the event horizon, you're in free fall. From your perspective, looking around at your immediate surroundings, nothing dramatic happens as you cross the horizon. There's no wall, no sudden jolt, no flash of light. You don't feel anything unusual. You simply continue falling, accelerating inward due to the black hole's gravity. The crossing is smooth and uneventful. This is one of the most counterintuitive aspects of black holes. We think of the event horizon as this momentous boundary, and from an external perspective, it is. But from the perspective of someone crossing it, the moment of crossing is completely unremarkable. You might even cross the event horizon without realizing it happened. There's no local marker indicating you are now past the point of no return. The geometry is smooth, the laws of physics operate normally, and nothing catastrophic occurs at that precise moment. Of course, this assumes the black hole is large enough. For a stellar mass black hole with an event horizon just a few kilometers across, tidal forces, the difference in gravitational pull between your head and feet, would tear you apart long before you reached the horizon. But for a supermassive black hole with an event horizon millions of kilometers across, tidal forces at the horizon itself are gentle. You could survive the crossing intact. This leads to a fascinating question. If nothing special happens locally when you cross the event horizon, why is it such an important boundary? The answer lies in what happens afterward and in how events at the horizon appear to observers outside. The perspective of an outside observer. Now, let's consider what someone far from the black hole sees when watching an object fall toward the event horizon. From the outside perspective, things look very different. Time dilation, the slowing of time in strong gravitational fields, becomes extreme near the event horizon. Imagine you're watching a spacecraft fall toward a black hole. As the spacecraft approaches the event horizon, its clock appears to tick slower and slower from your perspective. The light from the spacecraft becomes increasingly redshifted, stretched to longer, redder wavelengths. As the spacecraft gets arbitrarily close to the event horizon, the time dilation approaches infinity. From your perspective, the spacecraft appears to slow down, asymptotically approaching the horizon, but never quite reaching it. The image becomes dimmer and redder, eventually fading into invisibility as the wavelength of light stretches beyond what any detector can observe. In principle, if you could wait forever and had a perfect telescope, you would never actually see the spacecraft cross the horizon. You'd see it frozen at the boundary, eternally approaching, but never arriving.
This creates a strange dichotomy. From the infalling object's perspective, it crosses the horizon in finite time, perhaps seconds or minutes for a stellar mass black hole. But from the outside observer's perspective, the crossing takes infinite time. Both perspectives are valid within their own reference frames. This isn't a contradiction, it's a consequence of how time is relative in general relativity. There's no universal now that spans both reference frames. Events that are simultaneous in one frame are not simultaneous in another. This extreme time dilation has practical consequences. When matter falls into a black hole, external observers see it pile up at the horizon, taking forever to actually cross. The infalling matter becomes increasingly redshifted and dim. From the outside, the black hole appears to have a surface of frozen, redshifted matter eternally falling in. This surface is sometimes called the stretched horizon or apparent horizon. It's not the true event horizon, which is defined by the geometry of spacetime, but rather the effective surface visible to outside observers, composed of all the matter that's ever fallen in, frozen at the moment just before crossing. Spaghettification, tidal forces. While nothing special happens at the event horizon itself from a local perspective, we should discuss what does happen to objects falling towards smaller black holes, tidal forces. Tidal forces arise because gravity weakens with distance. The side of your body closer to the black hole experiences stronger gravity than the side farther away. This difference in gravitational pull creates a stretching force. Near a stellar mass black hole, these tidal forces become enormous even before reaching the event horizon. The gravitational gradient is so steep that the difference in pull between your head and feet, just a couple meters apart, could be millions of times Earth's gravity. This would stretch you vertically while compressing you horizontally, like pulling on a piece of taffy. The technical term is spaghettification, and it's exactly as unpleasant as it sounds. Long before reaching the event horizon of a stellar mass black hole, any extended object would be shredded into a stream of atoms. However, tidal forces depend on the curvature of space, and curvature at the event horizon decreases as black hole mass increases. For a supermassive black hole, the event horizon is so large and the curvature so gentle that tidal forces at the horizon are actually quite mild. For the supermassive black hole at the center of our galaxy, Sagittarius A, an astronaut could cross the event horizon experiencing tidal forces less than Earth's gravity. They would survive the crossing completely intact. Of course, they'd still be doomed. Tidal forces increase as you fall deeper, and eventually you'd be destroyed. But the crossing itself would be survivable. This highlights an important distinction. The event horizon's significance is geometric and causal, not related to the strength of physical forces at that location. For large black holes, the physics at the horizon is relatively gentle. The point of no return is defined by the warping of space-time, not by some violent physical effect. Time and space swap roles. Now we come to one of the strangest aspects of crossing the event horizon. Inside the horizon, time and space swap roles. This requires some explanation. In normal space-time, time points toward the future and space points outward in all directions. You can choose to move left or right, forward or backward, up or down in space, but you can't choose to move backward in time. You're always carried forward into the future. Mathematically, this distinction comes from the metric, the equation describing the geometry of space-time. In the Schwarzschild metric for a non-rotating black hole, there are two key coordinates, t, time, and r, radial distance from the center. Outside the event horizon, t is time-like, and r is space-like. This means t increases into the future, and r represents spatial direction. You can move inward or outward. But inside the event horizon, these roles swap. The coordinate r becomes time-like, and t becomes space-like. What does this mean physically? Inside the horizon, moving towards smaller r toward the singularity is like moving forward in time. It's not something you can prevent or resist. Just as you can't stop yourself from moving forward into the future in normal space-time, once inside the horizon, you can't stop yourself from moving towards smaller r. Reaching the singularity at r equals 0 isn't a choice. It's as inevitable as tomorrow. You can maneuver to delay it slightly, pointing your rocket engines to slow your infall, but you can't avoid it. The singularity isn't a place in space that you might avoid by steering around it. It's a moment in your future that you'll inevitably reach. This is why escape is impossible from inside the event horizon. Moving outward, back toward larger r, would be like moving backward in time, prohibited by the causal structure of space-time. For an outside observer, the singularity exists at the center of the black hole, but for someone who has crossed the horizon, the singularity is in their future. It's when, not where. Hawking radiation and the horizon. Now let's bring quantum mechanics into the picture because it reveals something remarkable about event horizons. They're not completely black. In 1974, Stephen Hawking discovered that black holes emit radiation. This seems to contradict the definition of a black hole. Nothing can escape from inside the horizon. But Hawking radiation doesn't come from inside the horizon. It comes from near the horizon as a consequence of quantum field theory and curved spacetime. Here's a simplified picture of how it works. In quantum mechanics, empty space isn't truly empty. It's filled with quantum fluctuations, pairs of quantum virtual particles and antiparticles that constantly pop into existence and immediately annihilate each other. Near the event horizon, something unusual can happen. A particle-antiparticle pair can form, with one particle just inside the horizon and one just outside. The particle inside falls into the black hole and can never escape, but the particle outside can escape to infinity. From a distant observer's perspective, it appears that the black hole emitted a particle. This is Hawking radiation. The black hole loses mass equal to the energy of the emitted particle. The temperature of this radiation is inversely proportional to the black hole's mass. For stellar mass and supermassive black holes, the Hawking temperature is incredibly small, far colder than the cosmic microwave background. These black holes are actually absorbing more radiation from the universe than they emit.
But for very small black holes, the Hawking temperature would be high. If a tiny black hole existed, say with the mass of a mountain, it would be hot enough to glow brightly and eventually evaporate completely as it radiated away all of its mass. Hawking radiation implies that black holes have temperature and entropy. The entropy of a black hole is proportional to the area of its event horizon, not its volume. This is the famous Bekenstein-Hawking entropy, and it relates the thermodynamics of black holes to the geometry of spacetime. The fact that entropy is proportional to area suggests something profound. Perhaps the information content of a black hole, everything that has ever fallen in, is somehow encoded on the event horizon, like information on a hologram. This idea has evolved into the holographic principle, one of the most important concepts in theoretical physics today.
The information paradox. Hawking radiation leads directly to one of the biggest puzzles in theoretical physics, the black hole information paradox. Here's the problem. In quantum mechanics, information is never destroyed. If you know the complete quantum state of a system at one time, you can, in principle, calculate its state at any other time. The evolution of quantum systems is unitary, meaning information is preserved. But what happens when matter falls into a black hole? The matter carries information, the quantum states of all its particles. If the black hole eventually evaporates through Hawking radiation, what happens to that information? Hawking's original calculation suggested that the radiation is purely thermal. It depends only on the black hole's mass, not on what fell in. If this is correct, then the information about what fell in is lost when the black hole evaporates. This violates unitary, contradicting a fundamental principle of quantum mechanics. This is the information paradox. Either information is lost, violating quantum mechanics, or information somehow escapes, violating the principle that nothing can escape from inside the event horizon. For decades, this paradox remained unresolved, with physicists split between those who believed information was truly lost and those who insisted it must be preserved somehow. Recent work suggests that information might be preserved, but in a way that requires rethinking what happens at the event horizon. The leading candidate is that information is encoded in subtle correlations in the Hawking radiation, correlations that would be undetectable with normal measurements, but that, in principle, preserve all the information. This requires that the event horizon be more complicated than a simple boundary. There might be quantum hair, subtle quantum information encoded in the geometry near the horizon, or the infalling matter might become entangled with the outgoing Hawking radiation in ways that preserve information. Some proposals go further, suggesting that the event horizon might have a firewall, a region of extreme energy that destroys anything crossing it, incinerating infalling matter and releasing its information into the Hawking radiation. This contradicts the equivalence principle, the idea that nothing special happens locally at the horizon, and remains controversial. The information paradox is still an active area of research, connecting quantum mechanics, general relativity, thermodynamics, and quantum information theory. It's a problem that has driven some of the deepest thinking in theoretical physics for the past 50 years. Inside the horizon. The journey to the singularity. Let's return to the perspective of someone who has crossed the event horizon. What would they experience on the journey to the singularity? First, the irrevocability becomes absolute. Every trajectory, every possible world line now points towards smaller r. You could fire your rocket engines at maximum thrust, but at best you'd slow your infall slightly. The singularity in your future grows closer with each passing moment. As you fall deeper, tidal forces intensify. Even for a supermassive black hole where the crossing was gentle, the curvature increases as you approach the center. Eventually, tidal forces become strong enough to tear apart any structure. Interestingly, the time it takes to reach the singularity after crossing the event horizon is finite and relatively short. For a stellar mass black hole, it might be a fraction of a second.
For a supermassive black hole, perhaps minutes or hours, a surprisingly short time given the enormous size of the black hole. What would you see? Light rays follow curved paths in the warped spacetime. Looking outward, you might see the universe compressed into a shrinking circle of light behind you, increasingly blue-shifted as you fall. Looking inward toward the singularity, space-time is so warped that visualization becomes difficult. Our intuitions fail in such extreme geometry. Some theoretical models suggest you might see images of all the matter that has ever fallen into the black hole, frozen at the moment just before it reached the singularity. Others suggest you'd see effects from the singularity itself, though what that means is unclear since we don't understand the physics at the singularity. And then you reach it, the singularity, the point where space-time curvature becomes infinite, where the equations of general relativity break down, where our current understanding of physics ceases to apply. We don't know what actually happens at the singularity. General relativity predicts infinite density and infinite curvature, which is physically nonsensical. Most physicists believe this signals that general relativity is incomplete, that at such extreme conditions, quantum gravity effects become important and might resolve the singularity into something less pathological. But we don't have a complete theory of quantum gravity. String theory, loop quantum gravity, and other approaches suggest different possibilities. Perhaps the singularity is replaced by a Planck scale structure. Perhaps it connects to another universe through a wormhole. Perhaps time itself ends there. The honest answer is, we don't know. The singularity remains beyond our current theoretical reach. Rotating black holes, the inner horizon. So far, we've discussed non-rotating black holes, which have a single event horizon. But most real black holes rotate, and rotating black holes are more complex. A rotating black hole, a Kerr black hole, has two horizons, the outer event horizon, which works much like the Schwarzschild case, and the inner Cauchy horizon. The region between these two horizons is the ergosphere. In the ergosphere, space-time itself is dragged around the black hole in the direction of rotation. You couldn't remain stationary in the ergosphere even if you tried. You'd be swept around the black hole by the rotating space-time. But you could still escape from the ergosphere. The outer event horizon is still the no-return point. Inside the outer horizon, things become strange. The inner Cauchy horizon represents another boundary. Crossing it leads to even more exotic regions of spacetime, potentially to regions where time travel becomes possible or where spacetime structure becomes highly unstable. However, most physicists believe the inner horizon is unstable. Infalling matter and radiation accumulate there, and in realistic scenarios, the infinite blue shift of this accumulated energy likely destroys the inner horizon structure, replacing it with a singularity or some other extreme region. Rotating black holes also have a ring singularity rather than a point singularity, a ring-shaped region where curvature becomes infinite. The structure is even more complex than non-rotating black holes, and our understanding even more limited. Quantum gravity at the horizon. Everything we've discussed so far is based on classical general relativity, with Hawking radiation being the main quantum effect. But there's growing suspicion that quantum gravity, the marriage of quantum mechanics and general relativity, might change our understanding of what happens at the event horizon. In quantum gravity, space-time itself becomes quantized. At the Planck scale, about 10 to the negative 35 meters, space-time might be discrete rather than continuous, or it might fluctuate wildly due to quantum uncertainty. Some approaches to quantum gravity suggest that the event horizon might not be as sharply defined as in classical general relativity. It might be fuzzy or fluctuating. Information might leak across the horizon through quantum tunneling effects.
The holographic principle suggests that all the information about the interior of a black hole is encoded on its surface. If this is literally true, then perhaps the event horizon is the fundamental object and the interior is somehow emergent or illusory. String theory has its own perspective.
Black holes in string theory are composed of D-branes and other exotic objects. The horizon might be understood as a collection of these stringy constituents, with information preserved in their microscopic degrees of freedom. Loop quantum gravity approaches the problem from a different angle, quantizing space-time geometry directly. In this picture, the singularity might be resolved into a high-density but finite region, and the horizon might have discrete quantum structure. These ideas are speculative and not yet fully developed. We don't have a complete, tested theory of quantum gravity, but they hint that our classical picture of the event horizon might be an approximation of something more subtle and complex. Observing event horizons. Given everything we've discussed about the strange nature of event horizons, can we actually observe them? Directly observing an event horizon is challenging because, by definition, no light comes from inside. But we can observe the region just outside the horizon. The Event Horizon Telescope collaboration has produced images of the regions around supermassive black holes, most famously the black hole in M87. These images show a dark central region called the black hole shadow, surrounded by a bright ring of emission from hot gas in the accretion disk. The shadow isn't exactly the event horizon. It's slightly larger, about 2.6 times the Schwarzschild radius for a non-rotating black hole. This is because light rays that pass close to the horizon are bent by the black hole's gravity, causing photons to spiral inward rather than escaping. The shadow represents the region from which no light can escape directly to the observer. Still, observing this shadow confirms predictions about the size and shape of the event horizon region. The fact that the shadow exists and has the predicted size is strong evidence that event horizons exist and that general relativity accurately describes the geometry near them. Gravitational wave observations provide another probe. When black holes merge, the gravitational waves encode information about their masses and spins, which determine their event horizon sizes. The post-merger ring-down, the settling of the merged black hole, depends on the properties of the newly formed event horizon. These observations are consistent with general relativity's predictions about event horizons. So far, we haven't seen anything that contradicts the standard picture, though efforts continue to test for deviations that might signal new physics. Philosophical implications. The existence of event horizons raises profound philosophical questions about causality, time, and the nature of reality. The existence of event horizons means there are regions of space-time that are fundamentally inaccessible to outside observers. No matter how long you wait or what technology you develop, you can never directly observe what happens inside an event horizon or retrieve information that has crossed it. This creates a permanent limitation on knowledge. Even in principle, even with infinite resources and time, there are facts about the universe that cannot be known to observers outside black holes. Some philosophers find this troubling. It suggests there are aspects of reality that are forever beyond empirical investigation. Others argue it's no different from cosmological horizons, regions of the universe so distant that their light will never reach us due to cosmic expansion. The event horizon also challenges our understanding of time. The fact that infalling observers experience crossing the horizon in finite time, while outside observers never see it happen, reveals how deeply relative the concept of simultaneity is in general relativity. And the information paradox raises questions about determinism and the fundamental laws of physics. If information can be destroyed in black holes, then the universe is fundamentally unpredictable. Knowledge of the present doesn't determine the future. This conflicts with our usual understanding of physical laws as deterministic. These aren't just abstract concerns. They cut to the heart of what science can tell us about reality and what fundamental principles govern the universe. So what happens at the event horizon of a black hole? Locally, for someone crossing it, nothing special. The crossing is smooth and unremarkable, following from the equivalence principle. From an outside perspective, objects appear to freeze at the horizon due to extreme time dilation, never quite crossing from the outside viewpoint. Inside the horizon, space and time swap roles, making the singularity inevitable, not a place to avoid, but a moment in your future. The horizon emits Hawking radiation, giving black holes temperature and entropy, and raising profound questions about information and quantum mechanics. The information paradox remains one of the deepest mysteries in physics, potentially requiring a radical rethinking of what the event horizon truly is. We've observed the shadows of event horizons with radio telescopes and detected their effects through gravitational waves. These observations confirm general relativity's predictions while probing for hints of new physics. But ultimately, the event horizon remains one of the most enigmatic features of our universe, a boundary where causality breaks, where time and space exchange roles, where our best theories face their most extreme test. It's a place of paradoxes and puzzles, where the clash between general relativity and quantum mechanics becomes acute, where our understanding reaches its limits. And that's exactly what makes it so fascinating. Thank you for joining me on this journey to the edge of what we can know. If you found this exploration valuable, subscribe for more deep dives into the frontiers of physics, and leave a comment. What aspect of event horizons surprises you most? Keep questioning, keep exploring, and never stop wondering about the universe's deepest mysteries.